I tried to also make my title of my talk as big a mouthful as what he just said, everything about me. So apologies for that. So thanks so much. I'm Jon Hyman, here to talk to you about how we model our schemas at Braze. But first, before we kind of get started, I'll just talk to a few of you for a brief minute or two about what it is that we do at Braze. So Braze is a customer lifecycle engagement platform. Our mission is to help brands use data to personalize and deliver brilliant customer experiences. So if you think about essentially the world in which customer brands live in nowadays, brands really need to understand the fact that they always need to be thinking about time. In particular, time to value their digital relationships with their consumers. When they're thinking about how to engage their customer base, always thinking about what's the time to get up and running, what's the time for me to get ROI on that. But also in today's mobile ecosystem, consumers are similarly thinking about time. They're thinking about it as like, what's the time I'm going to get value out of this brand, and my expectations as a consumer by the high levels of personalization that I'm going to expect and demand from brands I interact with. Because we're really kind of in this changing mobile ecosystem where computers are always on, always connected, and really enhancing our environment. And so it's very important for brands to think about this real-time nature, because when they collect data, in our opinion, it starts to lose value as soon as it's collected. It doesn't mean to say that historical data is not important, but just that when you get data from consumers, you need to essentially action on it in real time. And that's essentially what we help customers do. So at Braze, we work with some of the best consumer brands in the industry. You might have some of these brands or mobile apps in your pocket, like Lyft. If you've ever received a promotion from them, that's all orchestrated through Braze, or you get a push notification from Domino's Pizza letting you know that your order is on the way and coming to your door, that is also delivered through Braze. We work at a tremendous amount of scale. Across our customer base, we help engage more than 1.4 billion monthly active users every single month. We send upwards of 1.5 billion messages every day. So this talk's about 40 minutes long. We'll probably send something like 50 to 75 million messages during that time, maybe even to some of you in the audience during this talk. And we collect and process nearly 500 billion pieces of data from websites, mobile applications, email inboxes, and our customers' backends, and getting that over to Braze. So really what I want to talk to you today is about those messages and how our customers use our product to send them, but importantly, how we store that in MongoDB and translate that into ultimately what gets delivered on your phone or in your inbox. But before I start with that, I want to just first tell you a bit about how we use MongoDB overall at our company at Braze. So Braze is our primary database MongoDB is our primary database at Braze. And it's essentially used for most of our application models. We've got about 150 different types of collections, all of this stored in MongoDB, ranging from us storing the logins for our web dashboard all the way to the customer audiences that our customers end up defining. But if we look at where the bulk of all of this data comes from, it's in what we call a user profile. And what a user profile is that every time someone downloads a mobile application that Braze is in, we have an SDK that our customers put in their mobile applications or on their website. So when someone downloads a mobile app that we're in, or they visit a website that we're on for the first time, we create a user profile for that user. And what that lets us do is work with our customers to help define that user's unique, personalized, individual customer journey. What messages they're going to get, in what order, what channels, all of those different types of things. So across our entire customer base, we've got nearly 10 billion of these user documents that we're using MongoDB to store. So this requires an incredible amount of infrastructure. We have more than 1,000 shards to host all of this, and we spread that out on over 50 different database clusters in the United States and in Europe. In fact, in the United States, we're actually using custom hardware for our MongoDB installation. We've got PCI flash cards, and we've really been able to slice and dice up physical gear to get as high performant as possible. And the reason that that's important for us, and we'll get to this a bit later in the talk, is that for us, scaling is really all about read and write throughput. It's not so much about storage. We've got dozens of terabytes of data. It's a fair amount of data, but it's not something that I think is, you probably find other talks here who have a lot more than we do. But what's impressive at Braze is that our operations per second. We're processing over 250,000 operations per second, doing a lot of different reads and a lot of different writes. And there comes with a lot of challenges in order to focus and operate on this type of scale. And the reason that this challenge is difficult in general is because with us, we want to allow our customers to define and create customer audiences and target them for individualized messaging based on their demographics or any bit of their customer behavior. So what I just said, what I mean to say by that, is that all the data that we ingest on what consumers are doing in mobile apps, on websites, or responding to emails, is then going to be able to be used for segmentation and targeting and granular targeting at messages to then send to other individual customers themselves. So that means that everything we take in can be segmented on, which means we can't necessarily index or predict what all the data is we're going to get or what all the queries that our customers are going to want to send out. So from a database perspective, we lose the option for us to index on everything. So to compensate for that, there are a few things we can do. One is running on very fast hardware with very fast disks. Like I said, we have PCI cards. But RAM is another thing that we do. And we have a lot of RAM to run our queries. I mentioned we've got dozens of terabytes of disk, when we also have tens of terabytes of RAM that we're running in. And we really try to focus on what is the right RAM to disk ratio for us. And we always are constantly evaluating if we need to add more RAM to compensate for the fact that we need to just run faster. And the reason that we have to run faster is because our customers just frankly demand it from us. They want us to send their messages as fast as possible. When ABC News is sending a breaking news push, and they use Braze to do that, they want that to go to people's phones as fast as possible. And so we need to make sure that we can essentially deliver on that. Across our user base, our peak is in the hundreds of millions of messages sent per hour. And every single one of those messages requires us to do multiple reads and multiple writes. So we're doing billions of operations in Mongo every single hour. And so ultimately, we need to just be able to support that kind of scale as we grow. Lastly, we can't always predict what our customers are doing in our system. And what I mean by that is that our customers could create user audiences that we didn't anticipate them to do. And we want to protect ourselves against them being able to essentially break our system or slow it down by doing things that we didn't exactly anticipate. So what we do in terms of how we deploy our databases at Braze is we have a few different models. There's really three different things here. One is that we have a shared model, which is a classic multi-tenant setup. So for smaller customers that use the Braze product, we'll put them all in the same database. So some of you may do this yourselves if you run a multi-tenant app where you've got a collection and maybe you have like a customer ID field in that, and you've got the same data you've got data for multiple customers all in the same collection. We do that for some of our smaller customers. But as they grow, we can then start to move them around onto different databases and different clusters. So the second model we have is a shared database on a dedicated database on a shared database cluster. What this is we would build a Mongo cluster, say it has 20 shards, and then we might put 10 different customers on it. So there'd be 10 different databases on that MongoDB cluster. So there's some benefits to this. One is that now each database is logically separated from each other customer. The collections only contain the data for that customer and no one else. And then we have the opportunity to have a customer burst up to 20 shards or however many shards are on that cluster if they need to, even if in the average case they don't necessarily need that. So we can kind of pack them together that way. But we work with a ton of really huge customers like SoundCloud, Opera, the web browser. And for some companies like that, what we do is we build a dedicated database and we put it on a dedicated MongoDB cluster. So if I have 20 shards for SoundCloud, for example, all of their shards are dedicated to them, all the RAM is for them, all the CPU is for them, all the disk is for them. And so this allows us to handle how we scale. So there's some great benefits to this. I already just kind of mentioned that logically these things being separate is great for, it's actually great for security. But it allows us to have finer granularity over how we're going to scale. And so what we actually do is if our customer is starting to grow a lot, we can add more shards or we can actually move them over to their own cluster. And the way in which we've architected to do this is that we've built message processing and message sending servers in our services clustered around databases. So you can see kind of here in this illustration, these cogs represent processes that are either ingesting data, processing it, or sending messages. And what we can do is then pause those and effectively take a database down. Because we don't have one database, we don't have one single point of failure. If there's an issue that's happening for one of our customers, it can be isolated to them or that database cluster itself. Or if we're doing maintenance and upgrading versions or doing something else, we can keep all of our other customers online because they're not going to be affected since they're servers that may be stopped on their instance there. So that's essentially at a high level what we do with respect to storing those 10 billion user documents. But now I want to get into what is the meat of the talk today, which is the schemas around how we let our customers compose and then store the messages that they are ultimately going to send out. So the first thing that I want to do here is quickly just jump into the Braze product for just about a minute and just show you what it's like to be a customer of Braze and compose a message in our product. So what I have here is the Braze dashboard, and I'm composing what I'm referring to as a campaign. A campaign is a series of messages or a set of messages that can then be sent to a customer audience on some schedule. So here I have essentially my test campaign. I've called it MongoDB World 2018. And I have two different messaging channels. This campaign sends an Android push. It thanks some people for attending the talk here today. I could add images to this. I could add buttons. Really anything that you've seen in a push notification on your phone, our customers could add here and set that up. I also have an email message that's going out. And I've just taken the MongoDB World registration email and pasted it in here. But ultimately what this campaign would do is send this email with this subject line and this from and reply to alongside this Android push when it's going to be scheduled. So now that I have my messages that I've composed, the next part is to then set up how we're going to deliver it. And there are three different options our customers have to do so. One is what we call scheduled delivery, where they can choose to send a set of messages at a given point in time. It could be this Friday, it could be on the 4th of July, it could be right now, or it could be every day for 10 weeks. We have another type of schedule which is called action-based delivery. That is essentially where the campaign is going to be targeted and sent when a user performs some action. So if I wanted to send this message out to people who attended this session, I could simply just choose that here and ultimately send this message to users when they attend the session, an hour after they attend the session, or a day after they attend the session, whatever I would like, as well as then being able to then trigger it via API. We've composed all the messages, we've set a target audience, but the API is going to determine when we're going to actually send it out. The next thing is then being able to target an audience. And this is really where all of the special sauce and power of Braze comes into play. So I mentioned we have 10 billion user documents, and this is the interface that our customers have to then slice and dice their user audience up based on whatever demographics or customer behavior they want to then send and target. So this could be users who downloaded the app on the first day, who visited our website in the last week, who've made a purchase more than $100 in the last week. Anything that they want to target, they could do that here. And they do so by applying what we call a filter. So I've set up a sample audience here for users who are using MongoDB 3.4 or in the United States and Canada and are outside of Midtown Manhattan. But I could add really any of the hundreds of possible filter options that we have on customers' demographics or behavior. This thing right here is exactly why we can't index everything. We simply have too many different options that our customers can set up to create their audience segment on for us to be able to index every single possible one that our customers are doing. The last thing in campaigns is then assigning what we call a conversion event. Conversion event is a goal that allows our customers to tell us what the point of the campaign was. So then we can track analytics to see if users ultimately do that goal. So if I was sending this message to users who attended the session, I might set up a goal of I want users to rate the session, and I could see how many people rated the session after receiving the campaign within 3 days. And then if they were using Braze for A/B testing, which we're not going to get into in this talk at all, then we could do automatic intelligent selection on what variations of their message work best to drive the best versions. So that in a nutshell is essentially the Braze product. And everything that you just saw is modeled in MongoDB. That whole campaign object is going to be represented actually as one MongoDB document. And there are a couple of reasons that we decided to do this. First is just at a high level concept is that MongoDB, by using documents and not a relational schema, lets us model what can be a very complex object in one thing and store it as a document. So you saw a couple of different pieces here. We had messages, we had the delivery semantics, we had an audience space, we had conversion events. There's also all sorts of metadata like the name of the campaign. All that's going to go onto one MongoDB document. So when we map this back into our code, we use a lot of object-oriented design and a lot of inheritance in order to map these models from our database into our application. Now, I know some of you at first glance might originally think that one document sounds kind of crazy, but as we kind of go through this, we'll see that also because we use a highly object-oriented pattern, we can actually cache different sub-documents for performance such that we can get the benefit of both worlds. A large document that contains everything and easy to see at a glance, while also not needing all of the documents all at once. So we're now going to deep dive into each of these different categories and learn about how we actually store them in MongoDB. So the first bit is the messages. So in our code, we actually call a message an action. And that's going to represent the channel that you're sending. So we had an email and an Android push notification. So that would be like an email action or an action that then sends an Android push notification. But then the content of what is going to be sent out, the actual payload, we're going to call a message variation. So at a high level, the schema is going to be that a campaign object is going to embed many actions because it can have multiple messages. And then each message, each action, will then embed multiple message variations so that way our customers can define the payloads and later A/B test them. So what's cool about what we did is we use a lot of inheritance for this. So we have a lot of different channels. There's email, Android push, iOS push, Kindle, in-app messages, webhooks, TV messages, all these different types of things. All of those are going to be represented in our code as a subclass of action. And we can then further subclass them if necessary. So for example, you can see I've got push, email, and webhook. And then from push, we can break down to each of the different platforms. And we do the exact same thing with message variation. And you might ask, well, why are you even doing this sort of thing in the first place? And it really just comes down to the fact that each message type has a dramatically different set of fields that we actually care about. If we're looking at an Android push, we care about the text of the push. There might be a button, there could be a deep link into something in the mobile app. But if we're looking at an email, we care about the body, the subject line, the from address, the reply to. And if we're looking at in-app messages, we might care about the size of the in-app message, what that's going to say, any image assets and fonts that are necessary in it. And what's really great about Mongo is that it lets us store this separately, but in the same document, because we can essentially just embed these as sub-documents in a variation. So here I have on the right an example schema of what this might look like, where I have an array of actions, since we're embedding many of them. I can give the type in the document, which is going to signal to our code what objects to instantiate when we read it from our systems. And then an embedded array of message variations that then can contain the different fields that are necessary for that. So here's an example. We have an email message variation that again maps back into our code as an object that then has fields like subjects, HTML bodies, and from addresses. So that's just how we can store the messages together, and it's really great because again, like it allows us to take one document, have all the messages that it's going to send, and continue to then add to them if we essentially need to. And there are a lot of reasons why we might want to need to, and one of which is the fact that we deal in the age of mobile. And mobile is constantly changing. So we just had WWDC come out and talk about what's going on in iOS 12. And in iOS 12, Apple's adding some new things to push notifications. So then we're going to look at that and say, okay, what do we need to do and how do we need to change our schemas on our side? But what's great with Mongo is that the schemas are flexible. So we're not going to have to do migrations. We're not going to have to think about adding new tables. If you try to map out this type of schema in a relational model, I think it'd be very challenging because you've got half dozen or dozen or so different actions. They each have different options. And you really need to essentially make sure you get all the joins correct in order to pull everything back. But one way that Mongo has made it easy to extend is because we can just add fields to things. So when iOS 10 came out, all of a sudden you can now start sending rich images and media to iOS users in your push notifications. And we thought, well, this is cool. How do we build a feature about this? Like, what should we do to enhance just the standard offering? And what we decided to build was something we call push stories. It's essentially like a carousel of images you can send down to a mobile device and have them swipe through on the lock screen all these different images. We thought this would be really great for e-commerce customers. And in fact, this turned out to be really cool. We just got an example of this here. Right there is I could send down a push notification that has an image of Braze and an arrow. I could click it and then a picture of a cool like Iron Man-like robot that we could also send down and our customers could do whatever they want. But we did this in MongoDB, and we did it very, very easily because we were just able to extend the schema. So we created an object, a sub-document called a story page, and we just decided to embed many of them in the push message variation. So I ran out of my mic. Okay, great. So it's really cool that we can then have all these different layers of nesting. We've got campaign, action, message variation, and now push stories, story pages that we can all have again in one object for to think about the different tables that we would need there. So moving on from messages, the next thing that we saw was how we handle delivery scheduling. And again, 3 types of delivery schedules. One is scheduled, where a customer chooses and tells us when to send it. The second is when a customer can set it up to send the message based on an end user's actions. And then the third is based on an API triggering. So if we dig into how we store this in MongoDB, we use object orientation for all this as well. So if we look at a time-based schedule, I have something that represents like a Google Calendar-like thing on the top right. It's a campaign that sends every day at 9:30 a.m. Eastern Time, starting May 31st, and it goes for 8 days. We use a Ruby gem and a Ruby library called IceCube that can represent that concept. And we represent that as a YAML document, which you see on the bottom right here, which is the exact same YAML that represents the thing on the top right. And what we can do is serialize this between a string that we store in the database and then an object that the campaign is going to interact with. So again, in our actual application code, we're still going to be interacting with objects. And it's going to be storing that as a string in the database back onto the schema of the campaign. If we look at API triggered schedules, the way that this works is probably what you would expect, in that we assign an API identifier to a campaign when it's created, and then our APIs, upon getting validation and verification that it's the right authorized API key, we can just look up the API identifier and figure out what campaign we should then be sending. The really cool schedule, and the one that's worth talking about the most, is the way that action-based schedules work. So I mentioned again that this is when a user can cause a message to be sent based on a trigger. And we saw I wanted to send to people who attend a session. But not only can you use this schedule to trigger, you can also set up exception rules to cancel messages. So in my example I had earlier, I was, say, going to send a message to people who attended the session, and I was going to set my conversion event of people who rate the session. So maybe I want to send an email to people encouraging them to rate, but it's actually a bad customer experience if you've already rated something and then you get an email to rate. It's like when you bought something, and then you get an email that says, this is still in your cart, and you're like, no, it's not, I bought it yesterday. And so we want to avoid that kind of bad customer experience. So customers can configure exception events as well as the trigger events. And these events can be anything that a user could do. It could be using the application, visiting the website, entering a geofence, making a purchase, doing anything there. And so when we represent this back in our application, there's also a lot of inheritance at play, just like what we saw with the actions. So the campaign is going to embed a trigger schedule. So again, we've got embedding what's going to become an object. And the trigger schedule has some metadata, like the start times and end times, the delay, if we want it to send to you 2 hours after you've caused the trigger, 5 hours afterward, and whatnot, as well as then the exception event and the trigger event. And these are going to be embedded documents as well. So we've got a campaign that embeds a trigger schedule that's going to embed some more stuff. And the thing is that the campaign trigger event and the campaign exception event are very similar. They're both actions that a user could take. You could cause a campaign to be accepted out by visiting a website or entering a geofence or making a purchase. So we created one base class called tracked behavior base, which represents any of these user behaviors that we want to track and use as an action trigger. And then we have one subclass for anything that our customers could put on there. So we've got a subclass for using a mobile app, subclass for entering a geofence and whatnot. Again, we have got dozens of these in our actual application. And this is going to map back to a MongoDB document where we'll actually have one of these essentially embedded documents for each of these different types of triggers. So this again is really cool because each action has a different set of fields that it cares about. And so we can store that all on one document and not have to think about building out one new table per action type and all of that. It makes it really easy for us to interact with on a database level. So moving on from scheduling, I said that one of the hardest things that we do is the filtering and the target audience. So I want to spend about 3 or 4 minutes on that. So the way that user segmentation works at Braze is that our customers apply what we refer to as a filter. They apply a set of filters to create an audience segment. So in my example that we saw earlier, we were looking at folks who use MongoDB 3.4, are in the United States and Canada, and are outside of some geofence. It shouldn't surprise you at this point that we're using inheritance for this stuff as well. So we have a filter base class, and then we have hundreds of subclasses that represent each of those filters in our code. Each filter then can be represented as a MongoDB document. So if we look in the middle here, this is a slice of what the actual target audience looks like. We have an embedded array of filters. Each filter has a type that again tells our code what class to instantiate, and then it has the metadata that's associated with it to represent things like MongoDB version is 3.4 and users who are in the United States. Ultimately, these filters are going to translate into database queries. And this is where it gets challenging. Because if we start thinking about how we actually are going to do this without indexes, then we need to really figure out what's the best way for our product to actually work. So if I look at this simple MongoDB query, this is users who use MongoDB 3.4 and who are in the United States and Canada. Let's assume that I don't have a database index for this. Some queries we might have an index for, but some we just might not have it. Let's say we don't have one for this one. Now let's say that our customer has 10 million users. So of these 10 million, they have 10 million users in their database. We want to find users that match this. So what we actually do is we put a random number on every single document when we insert it between 0 and 9,999. So we have 10,000 of these random numbers. Each different one is on a document. So we at least now have an index on that. So then if you think about the fact that we've got 10 million users and we've got a random number on every single one of them, you could start thinking about bucketing your users up. So if I put them into 10 buckets, all the users who have a number between 0 and 999, all the users who have a number between 1,000 and 1,999, I can bucket that into 10 different buckets that each I would expect will have roughly 1 million users in it. It might not be perfect, but if the randomness is normally distributed, it should generally be close. So if I split it up this way, I can now start to parallelize my querying because I can take an unindexed query and target it against a subset of the collection. And so now I can turn one query that's unindexed into 10 queries that are unindexed, but that each scan a smaller portion of my database. And then why stop at 10? So we essentially could turn this into 30 or 40 or 50 or 100 different queries that we could all target at our database. And we could just modify the schema and the query a little bit to also include our random bucket ranges when we're doing a query. So I know what you're thinking right now is John, this sounds crazy. Why are you doing this? And there's a few reasons for that. One is that we want to focus heavily on parallelism. Now, an exercise that you could do is you could go on your laptop or on some computer and take any database you want. I don't care if it's Mongo or SQL or anything. Put 10 million users in it or 10 million documents in it or records or whatever you've got. Index it on something, and then make a database query that's perfectly indexed. Just make one of them and measure how fast it is you can return results back from the database. So when I've tested this, I've taken something that's perfectly indexed. In one database query, I'm returning 30,000 documents per second on that one cursor, which is pretty fast. But I mentioned earlier on that our customers want us to send messages as fast as possible. So if we can only even if it was perfectly indexed and we had one query and we were pulling things back at 30,000 per second, that means the fastest I could possibly send messages is 30,000 per second. And that's just not good enough. So the only way to get past that barrier is to now start to parallelize it and see if we can have multiple cursors returning multiple sets of data at once. We're able to pump out hundreds of thousands of documents per second into our system by doing things in parallel, even if it's not necessarily indexed. Another thing that's important to think about is randomness. So we care a lot about randomness at Braze. A/B testing is a huge part of what our customers do. And if we're randomly sampling 5% of a user audience, or we're setting something up that can only go to 1,000 people because it's a certain promotion, we want it to be a random 1,000 people or a random 5%. And if we run that experiment multiple times, we want it to go to another random 5% and not the same 5%. And so having a concept of randomness on our database becomes really, really important for us in general, which is part of what we get out of this. So then moving from here on to the last bit of what we saw on campaigns was conversion events. And conversion events allow us to track what is the end result or goal of a given campaign. And what's cool about this is that it's just anything like a trigger event or an exception event. You can set up a conversion event when users make a purchase or use a mobile app or do anything else like that. And so this is also just a track behavior base. So what's really cool about this by this point is we've got 3 things now that are all just the same thing. Conversion events, trigger events, exception events. In our code, they're the same object. In Mongo, they're the same subdocument from the look of it. They're just going to be embedded in different parts of the campaign, and that's where we get a lot of good polymorphism in our implementation. So to summarize all this stuff for campaigns, we talked about the fact that we use one document for all of these things, but you can see that we think about it in terms of each of these sub-documents and other patterns inside of it. And the reason that this is great for us is because campaigns can have hundreds of fields, and we're constantly adding to it all the time. But as long as we have a really good object relational model in our code, it makes it a little easier for us to interact with the database and then actually just have it be kind of a giant document there. When we look at a campaign, we do care about most of the fields. We want to know what channels does it have, what's the schedule, who's it going to send to. So we often want all of that data when we pull a campaign back, which made it a really great candidate for us to also just continue to embed everything. Now, I mentioned that we can still cache subdocuments and fields separately. We do a ton of this in our code. We often are caching schedules or audiences. We're caching the database queries that we're generating for filters so that we can do it in a performant manner. So I've shown you now one type of messages where you send a set of messages to consumers. But now really I want to show you how we can orchestrate an entire lifecycle of messages. And what I mean by this is something that is multi-step, multi-day, multi-message, multi-platform that really comprises an entire strategy. So you might see or have seen yourself receiving things like this. If you ever download a mobile application, you get something on day 1, then on day 3, then on day 10, then on day 30. This is the kind of lifecycle campaign strategy that I'm talking about. And we've built a product called Canvas to allow us to do that. And I'm just going to pop into Canvas real quick and show you what I'm working with. So here's Canvas. I'm going to zoom out because I'm on this laptop here. Canvas is an intuitive visual editing tool to create like a workflow of messages and a series of steps that you can put together to create a strategy. So what I have here, maybe hard to see because I've zoomed out a bit, is I'm first going to send an Android push notification to folks. Then I'm going to send an hour later an email to them, but I'm going to branch out and send people who are in Canada this email. And I'm going to take the people who are in the United States and I'm going to send them this email. This way I could put in appropriate country-specific things. I could then build this into another step where I could have it on essentially return back and send another push notification, an in-app message, another email, really any other kind of channel here. So what we've just created is we call a variation, a path that a user can go down. But we care a lot about A/B testing at Braze. And I said I wasn't going to get into it, but I'll show you just a little bit of it. Our customers are often testing and experimenting with different variations. So I'm going to clone this path we just created and set a 50-50 distribution. And now I have 2 paths of this strategy. And I could start experimenting with them. I could change the copy. I could change the time duration. Maybe I find that instead of sending the email an hour after the push, it's better if I send it the next day or 5 minutes later. I can start experimenting with all those different variables. So this is our product called Canvas that we use to help support these sophisticated lifecycle strategies. So we hop back into the presentation. Hopefully it's not going to surprise you folks that all of this is in MongoDB as well. And orchestration is like a series of campaigns, except that it has a little extra on top of it. Now, a canvas has paths that we just saw. So we're going to take our canvas object, and we can then start embedding many different path variations. And these have some metadata. We can name them. I set a 50-50 distribution, but you don't have to do that, whether it's a control or not. But then it links out to the first the first canvas steps that it's going to send to. And our customers have built some really cool canvases. We have some with hundreds of steps. We have some that go out as far as a year worth of messages that they're continuing to send and flow users down. It's really fascinating and exciting. And the reason that we use this foreign key relationship is because, surprise, canvas steps are just campaigns. And campaigns aren't campaigns, they're campaign bases. So we use inheritance here as well. So we have this base class called campaign base that then has a campaign and a canvas step, because canvas steps are very similar. Messaging, audience targeting, delays and scheduling, all of those things are important in Canvas just as they are in campaigns. So we can reuse the same database schemas and reuse the same application code in order to do that. So the way that Canvas works is that it's distributed and it's event-driven. So whenever our system is sending a message out to a user, we deliver a push to you or we send an email to you, our system fires an internal event that we call the received campaign event. You've received this campaign. We have processes that listen for these campaigns, and then with Canvas, they can look and see if you receive a message, if you're now supposed to receive the next step in that variation path that's going down. And if so, then we start scheduling out a message in order to then send that to you later. But ultimately, what's really cool about all of this is that Canvas is actually just a whole bunch of trigger schedules and action-based delivery. Because while we have those tracked user behavior bases of things like opening apps and using a geofence or making a purchase, we can also have one that's receiving a campaign, and it can all be completely identical to the way that all of our infrastructure works. So Canvas under the hood is just another identical Mongo document that you saw when we were working with campaigns. So I'm going to summarize here before we hop into some quick Q&A. Is at a high level, you can represent really sophisticated objects in MongoDB. It's straightforward, but I will say that this stuff is like challenging. It requires some careful planning. We didn't just get to this like on day one. We've been around for about 7 years or so, and you really got to think through what are the objects that you want to have in your code and how to map that back into your database. But documents are a great way to interact with this type of content that is often extended, that may require a lot of schema changes, or also where you care about a lot of different pieces of metadata all at once. So we do a lot of this with inheritance, and I would just, again, advise folks who are looking to do this to still need to think through what you're going to do. You can't just create a document and say, I'm going to slap more stuff on it, because you might find that you want to reuse things like we did with those track behavior bases. And embedding is a huge tool, and it's great, but also you should consider the full tool set of also foreign key linking like we do in Canvas when there's a lot of high pieces of links together there. It doesn't make sense to embed all the Canvas steps in one object because we could have dozens or hundreds of them. So ultimately, that's what I got in terms of how we do this at Braze. We are hiring, so I'll say, a guy, when you're on like Silicon Valley's intro, I feel like you could do whatever you want at a keynote, and that guy just kind of went for it. For those of you who know what I'm talking about. So we are hiring. Feel free to go to braze.com/careers if you're interested in anything that I said or any of the scale we're operating at. Love to talk to you more about it. And thanks so much. I think we got maybe 3 or 4 minutes, and I'll also be around after the talk for a few minutes too. Thanks.
Thank you, John. Appreciate it. We do have about 2 minutes, for 1 or 2 questions if you want, but yeah.
So the question was, what is the maximum document size we have? And it's 16 megabytes. So we learned this the hard way when one of our customers created an A/B test email campaign, and they put 16 megabytes worth of variations into it. And then we learned that we had to start limiting that. So we have seen ourselves go up against the limit. Using one document can also be a bane, as much as it can be a boon. And you just have to identify that and code around it. So the question was, do we store the images in PDF documents in the campaign? No, we do not. We have a CDN for all those things. They literally put 16 megabytes of HTML into the campaign. They did have, for what it's worth, 16 different variations, but they still want a megabyte per campaign. They needed to redo their HTML a bit. Yeah? What's the max number of parallelism you ever have to do? So the question is, what's the max number of parallelism that we do? We typically run with a minimum parallelization of 60, and roughly then the max, I think we jump up to about like 150. It can really depend on shard size, though, because if you do a lot of these unindexed queries at one, essentially, Mongo cluster at once, you can overwhelm it. So you need to kind of find a good balancing point. Yeah. So the question was, what's the memory to storage ratio I mentioned earlier? It is at a minimum 1 gig of RAM for every 10 gigs of disk. And then we have adjusted it up. I think in some cases we've seen like 5 gigs of RAM for 10 gigs of disk to do 50%. But and then in some cases, we have more RAM than we do disk, just so that way we can grow because we know we need to handle a large customer.
Fantastic. I think that's all the time we had. We really appreciate it, John.
Thanks, y'all.